All right, let's work through another example of block that includes block shear. We're also going to check tensile yielding and rupture in each plate as well. So here I have two plates, and I'm going to call them the bigger one A and the littler one B. And what you'll notice is they're the same width. This is 1/2 inch by 10 inches wide, the smaller one, and this is 1/2 inch. And I'm not even giving you a width, you just know it's wider. Right? So since it's wider, we're not even gonna bother calculating anything. So I have 3 limit states I need to check. I need to check tensile Oh, I did give an we'll give you a dimension here, 16 inches. I need to check tensile yielding, tensile rupture, and block shear both plates. Now, since they're the same thickness, plate B will be controlling, but we'll go through the exercise, right? Let's do A first. So if I go to chapter D, we have tensile yielding, which would be gross yielding on the cross section, right? Chapter D, please. Okay. Tensile yielding is phi Fy Ag. So let's see, phi TPN is, my phi is 0.9 for tensile yielding. I'm in chapter D, page 16.1-28. Fy A36. So Fy is 36 KSI, and my ultimate strength, if I go to the table 2-4, page 2-48. My FU, it says 58 to 80, so I'll just choose 58. So hopefully I'll give you guys a second to check that. But page 2-48, table 22-4 gives the yield stress and the tensile stress, the ultimate stress of all steel, well, most, so let's see, 36 KSI. My gross area is, 16 inches wide, and my plate is 1/2 inch thick. Right, 16 inches wide, 1/2 inch thick. So tensile yielding would be $259 kips. Tensile rupture. So tensile, pardon me, tensile rupture happens on a net area. Cross-sectional areas are reduced when you punch holes in them for bolts, and maybe other reasons. But none of those exist in this configuration. So, my net area, right, I'll say this, no holes in plates. Therefore, my net area is equal to my gross area. Right? Kind of makes sense? So, tensile rupture. I do have to have a U, right? But my shear lag factor, AE equals my shear lag factor times my net equals my shear lag factor times my gross, because there's no holes in the plates, right? So if I go look at my shear lag table D.3, shear lag factor. What shear lag factor do you think it would be? I'll give you a minute to read through, and look in your books too. But well, I hope you say case 1. It says all tension members where the tension load is transmitted directly to each of the cross-sectional elements by fasteners or welds, except cases 4, 5, and 6. All we have are 2 plates that are welded together. So as long as there's tension in the plate, there's no additional cross-sectional element to be not loaded, right? It's just on the plate. So we're in 1, and it says except cases 4, 5, and 6. Case 4 is plates where it's transmitted by longitudinal welds only. Well, we have transverse and longitudinal, so that doesn't matter. And then we don't have a round HSS or a rectangular HSS. So, yay, I get to use a shear lag factor of 1, which is super easy, and I don't have to go look stuff up, right? Case 1. Trying to make a number 1. So tensile rupture is 0 0.75 for my fee, right? That's back in Chapter D. Better make sure you know where that is. 58 KSI for my ultimate stress, my FU. Let me move that down a little bit. 58 KSI times 1 for my shear lag factor, and my gross cross-sectional area, 16 inches with 1/2 inch thickness. $348. So this thing is going to, this big plate is going to fail in yielding before it fails in rupture, is what that's telling you. And then finally, block shear. Block shear means that that a chunk of the big plate, right, is gonna break off. And it's gonna be this chunk that is 10 inches wide and 4 inches, right, 10 inches wide. It's gonna attach itself. It's like if we look at it in elevation, and this is my wider plate on the bottom, this chunk would like break out. I guess if you look at it, if after it's already broken, it would be like if, right? And it's got this little chunk underneath that you can't really see. Like underneath it is that little chunk that broke off. Block from 16-inch plate. So this is my tension plane, and I have 2 shear planes. So that's my only, right, one block shear configuration for this plate and for actually the whole, spoiler alert for the whole connection, right? So I need to calculate my gross shear, my net shear, and my net tension. Shear. Go back and scroll up a little bit, right? I have 2 shear planes. 1, 2, and they're 4 inches wide, 4 inches long, and the thickness is the thickness of the plate, right? So number of shear planes times the length of the shear planes times the thickness of the plate. So that is 2 times 4 inches times a half an inch, so it should be 4 inches squared. Right? I'm just doing that off the top of my head. Yeah. My net shear is equal to my gross shear, because again, I didn't have to pump. There's no holes, there's nothing to subtract out. My net tension is the width of the plate, so 10 inches. Right, the width of the plate here, that's bringing the chunk along with it. 10 inches, and the thickness of the plate beneath it, right, times a half an inch. So it's 5 inches squared. I have my 2 shear yielding and shear rupture. Let's see. Right, back in chapter J, phi times 0.6 yield stress, gross shear, my shear lag factor, which will end up being 1, my ultimate, and my net tension. What is this, 36? My gross shear, gonna say UBS is 1. Because the entire thing, right? If it's 1, even without, right? If it's 1 when you're doing regular rupture, it's 1. 58, right? And 5 inches squared. And that gives you 282. If we look at rupture, well, we'll figure out why rupture isn't getting control, but so any idea why rupture might not control? All right, this is shear, right? If I look, so shear yielding uses the gross shear area and the yield stress, which is always less than the ultimate. And then rupture uses the net shear area and the ultimate tensile stress. And in this case, my gross shear area is equal to my net shear area. So since my Fy is only 36 and my Fu is 58, this right here, 0.6 Fu A and V, the only difference is that stress, this is going to be greater than this, the 0.6 Fy AGV. So we'll calculate it, but it will not be controlling. Alright, my 58 KSI, 4 inches squared, 1 times 65 KSI, 5 inches squared. Why did I write 65? 58. It's back on the last one. $322 gips. So far, let's see what's controlling so far if we're just looking at that first plate. I've got 322, 282. Okay, well, that makes sense. Shear yielding is going to control over shear rupture. Tensile yielding and tensile rupture, 259. Let's see, 259 compared to 282. So far, 259. Tensile yielding in the big plate. Tensile yielding would control for the big plate. So now let's do the little plate. I'm going to let you guys do it on your own. Give you a few minutes. At least do tensile yielding and tensile rupture. We'll talk about block shear. Give you guys a few minutes to calculate that on your own. Okay. So hopefully that was a pretty quick calculation. It probably takes me longer to write it down. But let's see, tensile yielding. 0.7, or not 0.75, 0.9, 36 KSI. The gross area is 10 inches and it's a 1/2 inch plate. $162 kips, right? Tensile rupture, 0.75, 58 KSI, 10 inches and a 1/2 inch plate. Again, oh, and I guess a U of 1. We'll put that in there. My net area is equal to my gross area because there's no holes. My U is equal to 1 because you got transverse and longitudinal welds, and the entire plate is the only cross-sectional element. So 218 kips. Now what about block shear? Well, let's go back and look at the configuration. It makes sense that a chunk of the larger plate can break off in block shear, but if the same chunk of the smaller plate were to break off, it would just be tensile rupture, right? There's no shear planes. It would only be the tension plane. So block shear is not a limit state looking at the smaller plate, because again, it would only happen if this chunk broke off here and there's no corresponding shear planes that would break off. I hope that makes sense, right? Only that little chunk would break off and there's no shear planes corresponding to it. So let's look back. We have tensile yielding of plate B has 162, so that's the yield, that's the controlling one for plate B. If we go back and look, it makes sense. That's probably going to be ultimately the controlling one, the controlling design strength, because the one that controlled for plate A was also yielding, but it's a 16 inch versus a 10 inch plate, right? 259, 348, 282. So ultimately, right? smaller plate, plate B controls. So the limit state of this connection is 162 kips. Right, and that's looking at tensile yielding, tensile rupture, and block shear in plate A. Tensile yielding, tensile rupture, no block shear because it's not applicable in plate B. And plate B controls because they are the same thickness plate. If they were different thicknesses, right, if maybe it was an inch thick bigger plate or an inch thick inch thick bigger plate wouldn't make a difference. Inch thick smaller, less wide, narrower, the words I'm looking for, right? If it was like a thicker plate B, so less width but more thickness, then its gross cross-sectional area might be more, and it wouldn't be as obvious, but yeah, plate A was never going to control because it was the same thickness but wider. So that is how you can check those 3 limit states in a connection. You do have to check both, unless it was obvious, but we did it anyway just for fun. So that is a second example of checking the tensile strength of a connection in checking the cross-sectional or the connecting elements and then block shear of the yielding and rupture of the connecting elements and block shear of the connecting elements. All right, thanks.